Fluid kinematics. Fluid kinematics deals with describing the motion of fluids without necessarily considering the forces and moments that cause the motion. In this chapter, we introduce several kinematic concepts related to flowing fluids. We discuss the material derivative and its role in transforming the conservation equations from the Lagrangian description of fluid flow, falling a fluid particle, to the Eulerian description of fluid flow. We then discuss various ways to visualize fluid flows: streak lines, streamlines, path lines, timelines, and optical methods. And we describe three ways to plot flow data profile: vector plots and contour plots. We explain the four fundamental kinematic properties of fluid: motion and deformation, rate of translation, rate of rotation, linear strain rate and shear strain rate. The concept of vorticity, rotationality and irrotationality in fluid flows are also discussed. Finally, we discuss the Reynolds transport theorem, emphasizing its role in transferring the equations of motion from those following a system to those pertaining to fluid flow into and out of control volume. Lagrangian and Eulerian descriptions. So with a small number of objects such as billiard balls on a pool table, individual objects can be tracked. The subject called kinematics concerns the study of motion. In fluid dynamics, fluid kinematics is the study of how fluids flow and how to describe fluid motion. From a fundamental point of view, there are two distinct ways to describe motion. The first and the most familiar method is the one you learned in high school physics class: to follow the path of individual objects. For example, we have seen physics experiments in which a ball on a pool table or a puck on a air hockey table collides with another ball or puck or with the wall. Newton's law are used to describe the motion of such objects, and we can accurately predict where they go and how momentum and kinetic energy are exchanged from one object to another. The kinematics of such experiments involve keeping track of the position vector of each component. So in Lagrangian description, one must keep track of the position of A, B, C and the velocity of these particles as a function of time. When this method is applied to a flowing fluid, we call it Lagrangian description of fluid motion after the Italian mathematician. Lagrangian analysis is analogous to the system analysis that you learned in your thermodynamics class, namely we follow a mass of fixed identity. So this method of describing the motion of A, B and C object is not possible in case of fluid, because fluid contains number of particles. So from macroscopic point of view, interactions between parcels of fluid are not as easy to describe as are interactions between discrete objects like balls or air hockey pucks. Furthermore, the fluid parcels continually deform as they move in the flow. From microscopic point of view, a fluid is composed of billions of molecules that are continuously banging into another, somewhat like billions ball. But the task of following even a subset of these molecules is quite difficult, even for our fastest and largest computers. Nevertheless, there are many practical applications of Lagrangian descriptions, such as the tracking of passive scalars in a flow, rarefied gas dynamics calculation concerning re-entry of spaceship into Earth's atmosphere, and the development of flow measurement system based on particle imaging. A more common method of describing fluid flow is Eulerian description of fluid motion, named after Swiss mathematician Euler. In the Eulerian description of fluid flow, a finite volume called flow domain or control volume is defined. So this is your control volume here, and we define field variables functions of space and time within the control volume. For example, the pressure field is a scalar field variable for general unsteady three-dimensional fluid flow in Cartesian coordinates. So pressure field is equal to function of x, y, z and time. Then velocity field, which is a vector field variable, is a function of x, y, z, t. And then acceleration field is also a vector field variable, which is x, y, z and t. Collectively, these field variables define the flow field. the velocity field of equation, this can be expanded in Cartesian coordinates x, y, z, I, j, k. So v is equal to u, v, w. You can represent in terms of x, y, z and time. You can spread in terms of I, j, k. A similar expansion can be performed for the acceleration field. You can write in this method for this acceleration field. In Eulerian description, we don't really care what happens to individual fluid particles. Rather, we are concerned with the pressure, velocity, acceleration. So the difference between two descriptions is made clear by imagining a person standing beside a river, measuring its properties. In the Lagrangian approach, he throws a probe that moves downstream with the water. In Eulerian approach, he anchors a probe at a fixed position in the water. Acceleration field, as you should recall from your study of thermodynamics, the fundamental conservation law such as conservation of mass and first law of thermodynamics are expressed for a system of fixed density, also called a closed system. In cases where analysis of a control volume, also called an open system, is more convenient than system analysis, it is necessary to rewrite these fundamental laws into forms applicable to control volume. The same principle applies here. In fact, there is a direct analogy between systems versus control volume in thermodynamics and Lagrangian versus Eulerian description in fluid dynamics. The equations of motion for fluid flow, such as Newton's second law, are written for an object of a fixed identity taken here as a small fluid parcel, which we call as a fluid particle or material particle. If we were to follow a fluid particle as it moves around in the flow, we would be employing the Lagrangian description and equations of motion would be directly applicable. For example, we would define particles' location in space in terms of material position vector, x particle, y particle, z particle. However, some mathematical manipulation is then necessary to convert the equations of motion into forms applicable to Eulerian description. Consider, for example, Newton's second law applied to our fluid particle. So Newton's second law, that is force on particle is equal to mass of particle into acceleration of particle. So now acceleration of particle is equal to derivative of velocity particle with respect to time. So we had considered, suppose, this region in which the velocity field is modeled. We had taken this region. Now what is velocity of particle? That we know. At any instant in time, the velocity of particle is same as the local value of velocity field at the location. Means x particle, y particle, z particle. Means this is your particle. Mass of particle is given. X, y, z coordinate is given. And velocity of this particle can be calculated. So velocity is x particle, y particle, z particle. Now when you take the derivative, you will get this equation. Derivative of velocity with respect to time. Derivative of velocity, if you calculate with respect to x, then dx by dt, then del y by del y into dy by dt, and for the z, where del is the partial derivative operator and d is the total derivative operator. Now say rate of change of particles x position with respect to time, that is dx particle by dt. We can write it as u. Dy particle by dt we can write as v, and dz particle by dt we can write as w. So you can replace here u, v, w. So acceleration of particle x, y, z, t is equal to becomes dv by dt is equal to, if you replace here u, v and w, you will get this equation here. So acceleration of fluid particle expressed as a field variable. So this acceleration of particle can be expressed as del v by del t, and this can be represented v dot del into v, where del is gradient operator or del operator, a vector operator that is defined in Cartesian coordinate system. So gradient of del operator, del is equal to I del x by del x plus j del by del y plus k del by del z. The first term on the right hand side of equation, this term is called local acceleration. The second term is called a defective acceleration. So this term is non-zero for unsteady flows. The second term can be non-zero even for steady flows. So this is example here. Flow of a water through a nozzle of a garden hose illustrates that fluid particle may accelerate even in steady flow. In this example, exit speed of water is much higher than the water speed in the hose, implying that fluid particles have accelerated even though the flow is steady. We define steady in the Eulerian frame of reference to be when properties at any point in the flow field do not change with respect to time. Now in this case, since the velocity at the exit of nozzle is larger than that at nozzle entrance, fluid particles clearly accelerate even though the flow is steady. Note that while the flow is steady from the point of view of a fixed observer in Euler reference frame, it is not steady from the Lagrangian reference frame moving with a fluid particle that enters the nozzle and accelerates as it passes through the nozzle. Acceleration of a fluid particle through a nozzle. Nadine is washing her car using a nozzle similar to one sketched. Here, the nozzle diameter is on this side which is inlet is 0.420 inch. Nozzle outlet diameter is 0.182 inch and the length of this nozzle is 3.9 inch. The volume flow rate through this nozzle is given 0.841 gallon per minute and the flow is steady. Estimate the magnitude of the acceleration of a fluid particle moving down the center line the nozzle. The flow is steady, so you may be tempted to say that the acceleration is zero. However, even though the local acceleration del v by del t is identically zero for this steady flow field, the direction acceleration is not zero. We first calculate the average x component of velocity at the inlet and outlet of the nozzle by dividing volume flow rate by cross section area. So U inlet is equal to volume flow rate by area inlet, which is equal to, this is your diet inlet, you will get 1.9 feet per second. Similarly, the average outlet speed is U outlet is 10.4 feet per second. First is simple average value of acceleration. The acceleration is calculated based on the change in speed divided by an estimate of the resistance time. So del t is equal to del x by U average. So del x is given where U average is the average speed of inlet and outlet. So in this way you will get del t. Now we know from the definition of acceleration, acceleration is change of velocity, means at outlet velocity and inlet velocity, the difference of this velocity divided by total time, which is del u by del t. So U outlet minus U inlet by, this is your average time. So U average is U outlet plus U inlet and it will go in the upper side, denominator part. So this is your acceleration here. So this is your acceleration. The second method use equation for acceleration field components in Cartesian coordinates. So this is the equation for Cartesian coordinates. This component is 0 because it is steady. This component is 0 because the flow is in x direction. Z direction component is 0. So this will become U average into del u by del x. Now U average we have already calculated. It is inlet plus outlet divided by 2. And del u is equal to difference of inlet and outlet. And when you solve, this is your acceleration. So acceleration in this case is 160 feet per second square. Material derivative. The total derivative operator d by dt is given a special name. So this d by dt given a special name, the material derivative. Some authors also assign to it a special notation d by dt in order to emphasize that it is formed by falling a fluid particle as it moves through the flow field. Other names for the material derivative include total, particle, Lagrangian, Eulerian and substantial derivative. So if you use this material derivative with the velocity field, you will get material acceleration, which is here. If you apply this derivative on the velocity field, you will get material acceleration. This is your material acceleration here. This equation can be applied to pressure also. It will give material derivative of pressure, which is dP by dt, this equation. So this is about Lagrangian and Eulerian descriptions. Like this channel, subscribe. Thank you for watching this video.